Our first speaker is Santiago Rocha. He is a reservoir engineer at Cyrq Energy with a background in petroleum engineering and with specialized expertise in geothermal resource management. He currently oversees more than 70 megawatts of geothermal production at Cyrq Energy and is leading efforts in reservoir modeling, well testing, workover operations, and field optimization. He's experienced in integrating numerical simulations with operational data to improve asset performance, de-risk greenfield development, and support strategic decision-making, thus contributing to increased and more efficient power generation. He has also contributed to research in high enthalpy geothermal systems and closed-loop ideas. His topic today will be on the Thermo Hot Springs geothermal system here in Utah. So I will let him take it away, and I will just swap over to his presentation. Which one is it? This one, perfect. I'll just put it in presenter mode here. There you go.
All right. Thank you, Eileen, for the presentation. Thanks everyone for being here today, and thanks for inviting me to talk a little bit about the projects that we got in Utah and what we can develop, especially in that side of the state, right, which is known to have potential, as UGeN just mentioned, right? So here's a brief outline. When I sent the idea for the presentation to Eileen, I didn't think it was going to be that broad, so I'm going to touch a lot of information, but just in a high overview. You're more than welcome to give me more specific questions. Don't be too hard on my geology. I'm not a geologist. I'm a reservoir engineer. So, I'll walk you through the project, what we see from the geology and how we've integrated over the years and understanding the system and how to have a stable power plant for at least 16 years now. So today when I was reviewing the slides and trying to get my jargon right for what was going on from a geology standpoint, I came across these two nice maps that were presented in 1991 and 1994, which actually give us a pretty good background of the project location and what back in the days was previously done, and is still very, very accurate on the geothermal side and what's really going on in the southwestern part of Utah. So here you can see, let me see if I have a laser point. Where most of these anomalies are located, and it's basically that transition zone between the Colorado Plateau and the Basin and Range. It's still considered Basin and Range, but I don't think it's a coincidence that that's where you are seeing those geothermal expressions. And then, again, this is just a zoom-in version of what's really going on there in a different publication, and you can see where the Escalante Desert is at, where Thermo is at, and where we're going to talk a little bit more about this project. So now, going along on the slides from what we've done at Cyrq, I got to give credit a lot to Nolan Dellerman, who's actually the geologist who worked a lot in this project and who made this nice map. I think it was perfect to show up here with the DNR. I know you guys like maps. So the project location is here, again, in southwestern Utah. It's possibly what I believe the southernmost leg of the Pleistocene Lake Bonneville. I also believe it's not a coincidence that some geothermal or most of the basin and range geothermal projects are pretty close to the deeper basins of Pleistocene lakes, but that's another topic. And then it's part of the Basin and Range province, and then it's characterized by these extensional tectonics that allow heat flow and then opening for fractures. It's surrounded by the Mineral Mountains to the northeast, the Wawa Mountains to the west, and the Black Mountains to the southeast. And then it's just a flat basin with playa deposits, alluvial fans, and lacustrine sediments. Going a little bit further on the stratigraphy and the structural framework, it's fairly not complex. It's just your typical eastern basin range with quaternary, alluvial, and lacustrine deposits, tertiary volcanic deposits, Mesozoic and Paleozoic sediments, and some Precambrian basement with a granitic intrusion. That's probably the most exciting part of the geology out there. But besides that, it's your typical eastern basin and range. And then we do see some structural features that allow us to have the project or the geothermal expression, at least in the hot springs, right? And the main features are these northeast striking, west dipping normal faults, which are the ones that are aligned with the Thermo Hot Springs, which is the surface expression for this system. And then there are some other west-northwest trending faults that are actually defining structural boundaries, north or south, but we don't see them to be allowing a lot of flow within the system. Here is a gravity map, right? That was probably the initial or the basis of the initial development for this system. I just want to highlight that these are the wells that we are producing now, that we're producing since 2009, since the project started. It was hard, like for us coming in and trying to understand the project from zero, why these were the targets that they got, as we see most of the deformation and the structural features kind of to the west of it. But we believe, and we have a theory, that this gravity change was the reasoning why they decided to go there. But I'll dig a little bit on that, on what's really going on. So from conceptual hydrothermal model perspective, as I mentioned, there's a big hydrology and recharge that is evident and is coming from the mountain range that I just mentioned into the Escalante Valley. We estimate the recharge of, let's call it 20 to 40 kilograms a second. It's a decent recharge, and it's evident from the production temperatures that we see. I'll talk a little bit about it later on. And then we can see how that the pressure has been fairly stable for the project, and then supporting that theory of the recharge from the hydrology. The geochemistry and geothermometry had readings that range from 260 to 440 F. It's a wide range, and then actually I don't think it's a coincidence. It depends from where they were taking these samples. And it does indicate a lot of mixing from groundwater and very deep hot resource. And then, having all said that, and doing the structural framework and analyzing the system as a whole, we can see how the conceptual model comes from these two cross sections. This one that's D to D prime, and then that's E to E prime, and then D to D prime. So these two cross sections show what we believe is going on, and from the surveys and analyzing properly the resource, and you see. It's not your prolific upflow that probably you're seeing in the high enthalpy geothermal systems, but it still is showing you some signature going and pointing towards the hot springs, which is the surface manifestation of the system. And then you can see your sedimentary layers, and then having a polemic interval where we believe there's some movement going on that is actually cooling down or recharging the system. And that's what we believe is really going on. But then most of the movement is falling along this fault that's crossing the hot springs. So here I'm going to talk a little bit more about the power generation and the project as a whole, as Thermo Hot Springs. Back in 1776, it's believed that Fathers Escalante and Dominguez were the first ones to see the hot springs. But then if you've been there, you know it's a very remote area, and it was basically undeveloped, and back in the day it was just some nice hot springs. But then in the 1970s there were some TG holes and actually a deep exploration well that was mainly probably looking for oil and gas, and then the data you can find from it wasn't very exciting. We do believe that it wasn't that not that the temperature was there or the resource wasn't there. It was just basically that the well they flowed or analyzed the well wasn't the proper way as we do now with geothermal. Then in the 80s and the 90s, there were more surveys run, and then a better understanding of what was really going on and the signatures for the hot resource. With mixed geothermometry, as I mentioned, very broad from 287 to 392 degrees Fahrenheit estimated resource temperature. And then what led to the real development was in 2007, where a rancher called Mike Smith drilled shallow wells with temperatures of around 230 degrees F at nearly 500 F. So fairly good temperature, relatively shallow. And that's what gave the lead to the big development of the project. So right after that, 10 deep wells were planned and drilled. As I mentioned, we don't really know what targeting structures were they looking at, but they started drilling. And they had similar completions, and you can see that the temperature signatures weren't really convective. They were more conductive and not such as a prolific upflow, which is what we have hypothesized in the conceptual model. Right after drilling, they found fair PIs, but not your prolific permeability from the system. Still productive. The biggest surprise was that when they started producing the wells, although they were reaching temperatures all the way at almost 400 F, the production wells were producing at 270 degrees F, which confirms that geothermometry range and that highly mixing that we know is happening there. And so there's some cool down that is actually masking the hot, deep reservoir in the system. The initial design for the power plant was a modular design that wasn't pretty reliable. So the first 4 years of production weren't pretty great on the surface side. So the plant was then replaced for a modern ORC, and then the generation was ramped up from probably, I think I have here from 5 megawatts and to at least 7 or 8 megawatts net, the subtracting the parasitic load. And then that's sort of like the history of how the project was developed. Then again, right after the new replacement with the new ORMET unit, there was some reliable surface operation, but then you can see how the temperature started to decrease as you started pumping more and more water. At the time, they started getting concerned about this decline, so they decided to do some changes in injection and production. A lot of things were tested, even an EGS type of project, which was unsuccessful. But then they realized that if they were flowing less, somewhere closer to 6,400 GPM, the temperature was getting on a fairly stable manner. So they kept producing at that same flow rate. Actually, temperature decreased slightly, but then they hit a plateau, and they even got a heat up, which was exactly when we brought up one old producer that was not pretty hot, and they started injecting in there. Everything was fine there. Heat ups in any geothermal power plant are great, and maybe at the time we got really excited when a pump failed and they upgraded what was the biggest well in the field, with the consequence of increasing flow rate. And as soon as that flow rate was increased, the overall system started to go into heat mining, basically, and you could see how the decline started to go steeper, maybe steeper than this time frame. Then around 2022, when our team and the current Cyrq team got really worried because you're getting below 250 F of production temperature, and then you're just touching that base of actually power production. So we had to do something, right? So yeah, we need to do some action. So what we do is your overall resource management, and then just combining geoscience efforts and reservoir engineering efforts, trying to understand what are the structures that are there, which ones are open, which ones are not, your typical critically stressed faults, and then correlating that with PTA, PTS, flow surveys to understand how does the piping of the system, right? With that, we got the conclusion that yes, the temperature is down there, but then that polymictic interval is cooling down by a lot the system. So we found that at least 65 to 70% of the production is coming from a very shallow signature in that polemic interval. And then the remaining 35 to 30% of the hot system is what we're just targeting there. So we realized about it. We completed a new well right after that, just to target that deep hot zone. Just that followed that after a geologic and a conceptual model that was performed by the team. And then right after that, we were able to start mixing and changing the injection and production allocation. And that new well came up to have, I don't have the temperature here. The well came up to be 280 F, which was much hotter than the other wells, although the well was fairly shallow because we encountered issues drilling and we decided to leave it as it was, but it ended up having a much higher temperature than the other wells. Now the well is just like 4,000 feet. We believe that could have reached maybe 380, 400 F, but we did prove by stepping out a little bit to the west of the system that there's still resource out there. And it helped out a lot by increasing the inlet temperature by at least 8 degrees Fahrenheit. And it also improved the thermal decline from 2.3 degrees Fahrenheit a year to 1.3 degrees Fahrenheit a year. And that's how we operated over last year, back after 2023. Since that well came online, we were still not happy with seeing that big of a decline, and we ended up making some testing within the production. We know that the less we move from the legacy well field, the better the temperature response is going to be for the overall system. And we did some testing, and we ended up doing a preventive pump replacement. We didn't wait for the pump to fail. We just said, hey, let's instead of upgrading the pump, as usually sometimes it happens, we just downgraded it to slowly start decreasing the overall mass that we're moving in the system. And in our hypothesis, try to get a heat up. It's a little coincidence because I didn't want to show up this part at the end because I haven't been following a lot what's really going on, but it seems that it's working. And this is what's going on today. It seems to have at least heating up or maybe stabilizing and helping out the system. Talk to me in a year and see if where it ends. But that was what we ended up doing, and like just going back, doing your basic geology, understanding the system, and trying to optimize the geothermal production for the system, and it ended up being pretty well. And that's what we've done right now. Maybe I'm short. It went pretty fast, but I'll just do a brief summary of what I kind of explained today. It's a fairly mature field. It's been 16 years of operation. We've found that the production allocation plays a major role in the system, same as the injection. Also, that the hydrology is there is also important, and you gotta take advantage of it, and then also avoid it. To not tapping these colder parts of the resource. Then again, the production balance is paramount. You got to understand when you start heat mining, when you got that thermal breakthrough, and how to allocate injection and production. And then, doing your modeling from anywhere from your geology model to your numerical model, and going back and forth, and then understanding what's really going on. And it's an ongoing process. All models are wrong. Some of them are useful. I think we've created pretty useful models, but then still don't work. And something I really want to highlight whenever I talk about thermal is not your typical or your big 50 megawatt resource, but it's still been pretty stable over the years. And yes, it's 200 degrees Fahrenheit, and it's still a commercial project. The point I'm trying to make here is that you don't need to target always your 300F. You can still do something with low enthalpy, and I think that's where probably geothermal should be always looking at, not always hitting or trying to get 400F, right? And then from here, we see opportunities from the current plant, trying to keep up the pressure and temperature maintenance. It's always a perfect balance that you need to have in between. There's also some surface efficiency and equipment upgrades that we're looking at to capture a little bit more of generation and efficiency. And then keep proving additional resource. We stepped out, so to give you a perspective, this is the legacy field. So I'm comparing here what the reservoir model is telling us what the natural state looks like, and then how now with the injection and the production over the years, how that thermal breakthrough is coming in, and we're producing a slightly colder resource. And then the new well that we drill, going point towards to the west, was a little step out, and we proved that there is still resource. So trying to explore in between further and keep exploiting what we have with Cyrq in the lease acreage. And then there's also opportunities to do more subsurface stuff. I believe there's a potential on understanding geomechanics and seeing why the critical stress faults are there. How can you target those better, at least in this area? And then, keep feeding the geologic and conceptual model, drilling new wells, getting more geothermal megawatts in the grid, and that's what we are looking for now. And I think that's all I got for today.